Okay. All right. So last time we started talking about L and X type ligands and the covalent bond classification method and how you can use that to do electron counting. And, electron counting is really about deciding whether or not a molecule is closed shell, whether it has empty orbitals or not. And that dictates whether or not you can bind things to it. So, people generally don't think about the carbon in methane as being available for bonding. It's inert. But transition metals are not like that. They often have empty orbitals available for bonding. And so that means that you can bind stuff to them. And that's usually the first step in generating a reaction with a transition metal. Sometimes you have to dissociate something first. And that's often the first step in getting a transition metal to become reactive. If it has 18 electrons, it has a full valence shell. There's no room to add anything more. And you have to dissociate something before you can put something new on it. Okay, so that electron count tells you something about the reactivity of the compound and its availability to make new connections. So we went through a variety of examples. We pointed out how conjugated pi systems like allyl, cyclopentadienyl, benzene, cyclohexadienyl, the number of electrons those pi systems add to the metal center is equal to the number of carbons that are making connections. So allyl has 3 carbons that bind. Cyclohexadienyl has 5. Cyclopentadienyl has 5. So then we showed one crazy example of trimethylene methane. Same situation, 4 carbons, 4 electron donor. We started talking about compounds with a negative charge and how you have to add an electron for each negative charge. Or you can play a trick where if you want to count the total charge, you can pull off an anionic fragment to generate a neutral fragment and count the neutral fragment, and then think about the anionic piece that you pulled off as a 2-electron ligand. Like a cyanide anion is like a 2-electron ligand with a negative charge. So you can play games like that to make life easier. And we'll see another example of that today. And then we talked about metal-metal bonds. When 2 metals come together, they share electrons. Each metal raises the electron count of the other one. So you can do a trick where you count both metals at the same time and divide by 2 in a metal-metal bonded complex, if it's symmetric. And in that situation, you have to count the metal-metal bond as 2 electrons. Or you can count 1 fragment and then think about the other fragment as a 1-electron donor in that metal-metal bond. So let's do some more complicated examples of that today. Okay. So let's take a look at this osmium complex, osmium 3, carbon monoxide 12. This is a triangular complex. And each of the osmiums has 4 carbon monoxides, 2 metal-metal bonds. So each osmium is octahedral in this compound. Now, one way to do this would be to count each individual metal center. Let's do osmium A. This guy has 8 electrons. It's bonded to 4 COs. That gives you 8 more. And then it has 2 osmium ligands. And that's 2 electrons. Each osmium center donates 1. And that gets you to 18. Or you could say you have 3 osmiums, 12 COs, and 3 osmium bonds. So 3 times 8 electrons for osmium, because osmium is in the iron, ruthenium, osmium column. 12 COs is 24, 2 electrons per CO. Now, how do we count the osmium-osmium bonds here? Each osmium-osmium bond is counted as 2 electrons in this case. And that gets you to 54 electrons for 3 osmiums is equal to 18 electrons per osmium. Okay, so that's a nice closed shell cluster. So let's do another example here. Now we're going to look at some bridging ligands. We'll start off with another metal-metal bonded complex. Rhodium 3, mu2CO, 3 times, A5, C5H5. What does that mean? What does mu2CO mean? That means bridging 2 metals. Mu2 means bridging 2 metals. A5 C5H5 is what ligand?
Cyclopentadiene.
Cyclopentadienide or cyclopentadienyl. Makes 5 connections. Sorry, there are 3 of these guys. I left off a 3 there. So you got a trirhodium complex with 3 cyclopentadienyls and 3 mu2COs. What does that thing look like? Any guesses? Mu2 looks like that. That's a mu2CO, and there are 3 of them. So let's give this one an A, a B, and a C. So rhodium A has 9 electrons because it's in the cobalt, rhodium, and iridium column, which is just to the left of nickel, palladium, platinum, and just to the right of iron, ruthenium, osmium. So we have a rhodium B in here, and we have a rhodium C in here. Each one of those guys is going to contribute an electron. Rhodium A has a CP ligand. How many electrons for the CP ligand?
5? Is it 5?
5 electrons, 1 for each. And rhodium A has 2 mu2 COs. Now, how much do those things contribute? So I'll tell you, there are 2 electrons here. And it's really like 2 times 1/2 times 2. In other words, there are 2 electrons per carbon monoxide. That's all CO has to give. Okay, but it's splitting them between 2 metals. So you take those 2 electrons and you divide them in half evenly. And then there are 2 of those ligands. I look at that carbon monoxide ligand, and to me, it looks like a ketone, right? With 2 rhodiums stuck to it. So you can think about each of those metal carbon bonds as just like any other X-type bond. So you could also, in principle, do 3 rhodiums is 27 electrons. 3 mu2 COs is 6 electrons, 2 for each carbon monoxide. That's all CO's really got to give here. And we have 3 CPs, that's 15. And then we have 3 rhodium bonds, that's 6. And well, we forgot to do the math on this one too. This is 18 electrons. This is 54 divided by 3 is 18 electrons each. Okay. Let's do this one again. This time we're going to go to a little harder version. We're going to go to iron 4, eta 5, C5, H5 4 times, mu3, CO 4 times. This is a little pyramid with CPs on each of the corners. Now we've got a mu3 CO. Where's that CO going to go? What does that mean, mu3? It means it bridges 3 metals. Each CO sits in the face of each of those pyramids. So let's do it from the perspective of one iron here. How many electrons for iron? Iron, ruthenium, osmium. They all have 8. One iron has got a CP, that's got 5. How do we do this mu3CO? Well, there's 3 of them, and there's 2 electrons spread between 3 metals. Two electrons that way. And then you have 3 bonded irons, and that's 3 electrons. That's 18 electrons. Or you could do 4 irons at 20, sorry. 32. You can have 4 mu3 COs. How many electrons do we do in this case? CO only has 2 electrons to give. So we're going to get 8. You got 4 CPs, that's 20. And how many metal-metal bonds do we have? 6 of them. 20, 20, 40 on top of 32 is 72. Divided by 4 equals 18. Okay. So I kind of like doing the total electron count and then dividing by 4 myself. All right, let's do another example. This time, however, it's going to be an asymmetric example. So we've got here this iron-nickel complex. So when things are asymmetric, you got to be a little bit more careful to decide who owns what. Okay, so let's do them together. We've got a nickel is 10, an iron is 8, a pair of terminal COs is 4. We've got a mu2 CO, that's 2. We have an iron-nickel bond. There's a pair of electrons in that. We have 2 CP ligands, that's 10. And the sum of those things is 36. Divide that by 2 equals 18 electrons per metal. Now let's count these guys separately. So we're going to do iron is 8. It has a CP ligand. That's 5. It has 2 terminal COs. That's 4. It has 1/2 of a mu2 CO, and that's like 1 electron from a metallo-ketone type of a picture. And then it has a nickel bonded, which we say is 1. We add these up and we get 19 electrons. Let's do the nickel. Nickel is 10, CP is 5, 1/2 mu2 CO is 1. We have an iron, it's going to contribute 1, and we get 17 electrons. So what's going on here? Tell me about this compound for a second. Does anybody want to explain what's going on with the electron counting? Does anybody see a problem? Why are these two numbers different? What does that mean?
What, does it mean that like the electrons between the iron and the nickel are both like changing in the molecule? Like they're going from, like if you look, it's like the iron is F8, is D8, and the nickel is D10. So the discrepancy is like 2 electrons, and then I look over here, I see Fe8 and nickel 10. I don't know what I'm talking about. I'm just trying to look at a pattern.
Well, let's take a look at the total electron count, Mac. What do you see here? We got 19 and 17 in the case of the iron nickel when counted separately, and then we have 18 per metal when counted together. Okay, so we got a different answer using the 2 different methods. That's one thing. The other thing is that 19 electrons exceeds the valence shell, right? So one of the, there's one more electron than 18 there. And you can't, you can make 19 electron compounds, but they're extraordinarily reactive. The compound that has 17 electrons could use an extra one, has space for one. And there's this metal-metal bond there, right? So it's sort of like, is there a metal-metal bond there? Who owns the electrons? Okay. And I would say, this compound is probably really iron plus and nickel minus. So you could imagine drawing a natural resonance picture here to fix this hypervalency issue. Push the electrons onto the nickel and make it negatively charged. Make the iron positively charged. Okay, so you got to be careful when their compounds are symmetric. The counting together versus separate thing can give you different answers. Let's do other bridging ligands here, including this rhodium complex. With bridging chlorides, rhodium A and rhodium B again. Now, how do you think about those chlorides? One thing you can do is to draw the molecule like this. Where you take a lone pair from one of those chlorines and donate it to the rhodium center. Right? We use the lone pairs to make pi bonding interactions, but they also can be used to make sigma bonding interactions with another metal. And that arrow represents a dative bond. The straight line represents a normal covalent bond. So a chlorine ligand like that can make an X interaction and an L interaction. And of course, the 2 chlorines are indistinguishable in this molecule. So there's also this resonance structure. Like that. So let's do rhodium A has 9 electrons and it has 2 terminal COs. Those are 2 each. It's 4 electrons. Now you can think about this as an X-type chlorine interaction, which is just a single X-type, 1 electron donor. And then there's this mu chlorine, which is an L-type. So that's 2 electrons. 16 electrons. Let's check the double version. This is a symmetric compound, so we're going to count them up completely. 2 rhodiums, 9 each is 18 electrons. We got 4 COs, 2 electrons each is 8 electrons. And now you have 2 mu2 chlorines with 3 each. An X and an L per chlorine gets you to 6. And that's 32. (16 electrons each). Okay. Bridging ones make an X, and then they use their lone pair to make an L. Let's do this again for another one, this iron compound. Tricarbonyl complex of iron with bridging phosphides. And this thing, it turns out, is 2-. Now here, you can think about this compound in the same way, and it sort of makes a little bit more sense, maybe. Because you're used to phosphines being L-type ligands. With the bridging phosphide providing an X to 1 and an L to 2. Now let's do something else a little bit funny. Let's dissociate, sorry, this guy is 2-, I can't forget that. Let's dissociate this compound for a minute, pulling apart the neutral and the anionic fragments. Well, how do we do that? One way is to pull off the PR2 fragment. As a negatively charged thing. So when you pull it off, PR2 is like NR2, right? If it has 2 things, it's going to end up with a negative charge, or it's going to be a free radical. So we can dissociate these things as 2 negatively charged pieces and leave behind a neutral iron tricarbonyl. And then you can think about this negatively charged thing as being able to donate its 2 lone pairs. And it's really easy to count iron tricarbonyl, right? That's 8 plus 6 is 14 electrons. And then each one of those phosphide anions donates 2 electrons to each metal. So you're going to get 4 more. That gets you to 18. So let's just do from the perspective of 1, we have an iron. We have 3 CO ligands. We have an X-type PR2 interaction. We'll call that 1. We have an L-type PR2. That's 2. And we have a 2- charge over 2 iron centers is 1. That's 18 electrons. So you can count it up that way. The bridging ligand gives an X and it gives an L. And you have to remember to deal with the charge and to split it in half. I kind of like the way on the right where we dissociate the PR2 fragment as an anion. And then think about that anion as a 2-electron donor. And that puts the charge and the bridging thing into a simpler space. Okay, let's do bridging hydride ligands. These are special. They don't have lone pairs. The hydrogen 1s orbital is spherically symmetric. And that makes it good at bridging. See a lot of bridging hydrides. So what's an example here of a bridging hydride? Well, one you're familiar with, I think. Two borons, two boranes getting together to make what's called diborane. That has a bridging hydride. Now, it's a little bit strange to draw a bridging hydride because you have two normal covalent bonds to an atom that only has one electron to begin with. So you can't make two normal covalent bonds with that one electron. So this, people refer to as a 2-electron, 3-center bond. The drawing makes it appear as though there are more electrons than there are. So this makes hydrides different than halides and phosphides. Okay, so how do you think about this? Well, that hydride can be thought about as a 2-electron donor. You can think about the BH interaction, the BH bond, as being a 2-electron donor to the other boron. So let's take a look at what that looks like. So we have a Lewis picture. That looks a little bit like this. Where each BH bond coordinates to the empty orbital of the other boron. You can also draw this as an MO. And how many, in one of these 2-electron 3-center bonds, how many orbitals are we mixing? You're mixing 3. You've got your boron and your hydrogen. And there's an all bonding combination. And there's an all anti-bonding combination. It's got 2 nodes. And the one in between has 1 node. And that 1 node is going to be symmetrically displaced I shouldn't have done that. Let's try that again. Two electrons available. So it's the totally symmetric combination of the hydrogen 1s and the two p orbitals on boron. So let's use this picture to do some bridging hydrides with transition metals. And we're going to look at this cool zirconium compound. Two bridging hydrides there. And you can also think about this thing in this way. Where each zirconium hydrogen bond is a 2-electron donor to the other zirconium. So if you dissociate this thing into two monomers, you got a 1 metal hydride bond that can be a 2-electron donor to the other one when you put them together. So each zirconium center contributes 4, has 2 CPs for another 4. It has an R group. What's an R group? Could be a carbon. Could be a hydride. Usually it refers to hydrocarbon in organometallic chemistry. So how many electrons for that? What if it's methyl?
1.
1 electron. The neutral fragment is a free radical. You have an X-type hydride, and then you have a zirconium hydrogen bond bringing up 2 electrons, and that gets you 18. Sorry, there's a mistake here. This should say 10. 2 CPs is 10. All right. Now, there's one tricky issue here, and it's pretty broadly tricky. So that's when you have bridging hydrides and metal-metal bonds in the same compound. So for example, this pentacarbonyl chromium hydride anion. You can think of this guy like this. So that bridging hydride there is acting as a L-type donor to the other chromium, but that seems okay. But what happened to the metal-metal bond? It's not drawn on the right. So let's see, let's count some electrons and try and make sense out of this a little bit more. So we'll do chromium A and B again. Chromium A contributes 6. has 5 carbon monoxides for 10. And we're going to give it the X-type hydride is 1. And there's a negative charge. Let's throw the negative charge in the mix for 1. Now let's do chromium B. 6 CO5, that's 10. What else does it have? It has a chromium hydrogen bond acting as an L-type donor, so we're going to give it 2. And both of these things add up to 18 electrons. Now note, I did not include a chromium-chromium bond in my electron count, and I got to 18. So that basically implies that the metal-metal electron interactions don't really add up to making a normal covalent bond. And this bridging hydride thing over there on the left is a little bit misleading. You know, it's drawn in this way where you get a triangle like that, when in fact there's no metal-metal bond at all. If there were a metal-metal bond, a normal covalent bond, then the electron count would be 1 electron higher for each chromium, putting you to 19. So that triangular representation up there is misleading. And in general, when you're looking at metal-metal bonded compounds, you want to try and assess that. How many valence electrons does the compound have? Does it exceed the 18 electron rule or not? And if it doesn't exceed 18 electrons, then you can add metal-metal bonds if you want. As long as there are electrons to use to make the bonds, you can add metal-metal bonds to raise the valence count. If you have more than 18, you can delete them. Now, another aspect of this problem is that we chose the negative charge to be on chromium A instead of chromium B. Had we done it the other way around, we would have ended up with a 19 and 17 electron situation again. So, you know, it's a little bit ambiguous, I guess I would say. This is a symmetric compound, so you can't really have 17 and 19. Doesn't make sense. Okay.
Is it possible that the negative charge is actually on the hydride and they just make 2 normal sigma bonds?
When you say it makes 2 normal sigma bonds, you mean the negatively charged hydride makes 2 normal sigma bonds?
Yes. It's like the hydride is in the middle of two metals. Right?
Yeah. Well, you know, if you take the drawing seriously, you cannot make 2 normal covalent bonds with the hydrogen.
But if you have the extra charge.
Even with that extra charge, so the normal covalent bond analysis and the X and L analysis is a neutral fragment picture. If you take a hydride anion and you analyze the bonding of a hydride anion, it has 2 electrons to donate in an L-type interaction sense. So, you know, you can't really make a second bond. I mean, I guess, you know, maybe it's just splitting hairs here because we're saying the chromium hydride electron pair acts as a 2 electron donor to the other metal center. So maybe that's similar to what you mean.
Okay.
Yeah, I guess that is. So that pair of electrons is raising the oxidation, raising the electron count of both chromiums. In other words, on the left and on the right, we're talking about the same pair of electrons and counting them for both metals, right? The upper portion chromium with 6 electrons and 5 COs is the same. We're just accounting for the hydride and the negative charge in this arrangement to get to 18 each. So yeah, you could think about the hydride anion donating electrons to 2 different metal centers, I guess.
Okay, thank you.
Okay, so we've started dabbling with the like negatively charged ligand thing. And that's going to be helpful because we're going to transition now to talking about formal oxidation state. Formal oxidation state tells you the charge on an atom, assuming that the electrons in the bonds are given to the more electronegative partner. Generally speaking, this is not how people do it. What they actually do is count the number of X-type interactions. This is equivalent to assuming that the ligand is negatively charged and the metal is positively charged. Relative electronegativities of bonded partners. But generally speaking, when people talk about transition metal complexes, it's generally assumed you have metal plus and ligand minus. And why do people assume that? Well, they assume the metal is more electropositive than the ligands, but that's not always true. But you can forget about that because people make this assumption all the time. And it's a bad assumption if you really want to know the charge on the metal and whatever. But if what you really want to know is the valence, which is what people are actually counting, and they report it as an oxidation state. Okay, so count the number of X-type interactions that determine the oxidation state. So let's do cobalt, dicyanide, carbon monoxide, bis triethylphosphine, anion. So we're going to assume any X-type ligand is minus, any L-type ligand is neutral. So we're dissociating everything as closed shell fragments here. 2 cyanides, 1 carbon monoxide, 2 triethylphosphines, yeah, and 1 cobalt. What's the charge on the cobalt? We pulled off 2 cyanide minuses from a 1 minus complex, so that cobalt is going to be +1. And so this is considered to be cobalt 1 with 8 d electrons remaining. It starts with 9, but it's 1 plus. So it's D8. Tris-triphenylphosphine, rhodium chloride, pretty famous molecule, Wilkinson's complex. Three phosphines, one chloride in a negatively charged state, leaving behind one rhodium plus 1. So this is rhodium 1, D8. Because cobalt, rhodium, and iridium all have 9 to start with. So cobalt, rhodium, and iridium 1 are D8. Let's do our nickel bis pi allyl. We're going to break this apart into allyl anions. The lone pair on carbon. And that gives you 1 nickel 2 plus. 2 anions coming off. Closed shell. So this is nickel 1. Nickel 2. How many electrons are left? Nickel, palladium, and platinum have
8, like so 10.
10 electrons to begin with, and it becomes D8 when it's nickel 2. How about that cyclopentadienyl molybdenum? Pull off the cyclopentadienide closed shell anion. That's a good anion, right? It's aromatic. It's convenient to pull off cyclopentadienide anion. It matches very well-known closed shell structure. We've got 3 COs. You've got a hydride. So what's our molybdenum center? What's the charge there? 1 hydride anion and 1 cyclopentadienide anion leaves behind a molybdenum 2 plus. So this is Moly 2 D. Starts off with 6 electrons. It ends up with 4. Chromium, molybdenum, and tungsten. Chromium, molybdenum, and tungsten have 6 to begin with. So molybdenum 2 plus is D4. All right, so that's all pretty hunky-dory, but I'll tell you, it's not always hunky-dory. Let's take a look at some carbene ligands here. I love carbene ligands. They are fun. There's 2 kinds. Again, complexes and ligands named after famous inorganic chemists, kind of like named reactions or something from an organic chemist. This is a Schrock type carbene after Dick Schrock, Nobel Prize winner. Where's the carbene? The carbene is that CH2 there. People call that a Schrock type carbene. So we've got a CP anion coming off of this thing, actually two of them. You've got a methyl coming off. And what do we do about that CH2? How do we count it? Well, each of these CPs contributes 2 X-type interactions. Okay, each methyl contributes 1 X-type interaction. How many X-type interactions for this CH2? Carbon makes 4 bonds. So that double bond is equivalent to a 2X situation. And so you can think about this thing as a 2- fragment. So we add up those interactions and you've got tantalum 5 plus. So tantalum 5, how many electrons are left? You have to know your periodic table. Vanadium,
0.
niobium, tantalum leaves behind 0. Those are D5 to start with. Let's count the electrons here. 2 CPs is 10, tantalum is 5, CH3, how many electrons does CH3 contribute in the covalent bond classification scheme where we count everything as neutral ligands? 1. CH2, we said is 2 X-type interactions. So it contributes 2 electrons. And that gets you up to 18 electrons total. Okay, so it turns out that this thing is like CH2 2-. It's nucleophilic at the carbon. The carbon is a powerful donor. That's a Schrock type. Let's do a Fischer type. Here, we're going to take this pentacarbonyl complex of tungsten. And it has very interesting methoxy and a phenyl substituent on this carbene carbon. Now, this compound has another resonance structure that looks like this. Oxygen plus. So what we've done here is we've taken the electron pair from oxygen and pushed it onto the carbon to make a carbon-oxygen double bond. And then we've pushed the electron pair from the metal-carbon double bond onto the metal. So this oxygen and the tungsten center are kind of at opposite ends of a conjugated network, pushing back and forth on each other. And you note there that carbon, if there are 5 carbon monoxide ligands around the tungsten, those are electron withdrawing in a pi symmetry sense. And that helps to stabilize that negative charge on the tungsten center. So a Fischer carbene complex of that kind is kind of, the DAC is stecked. The deck is stacked. The deck is stacked. Okay. Now let's count these here. We've got 5 COs is 10 electrons. We got a tungsten, which contributes 6. And we have this carbene. 2 X-type interactions in this representation. That gets you to 18 electrons. Now, let's draw this thing. We got 5 COs, nothing's different here. 10 electrons. We've got a tungsten, that's 6. But now there's a negative charge. We've got a negative charge on the metal. Got to add one. And how do you handle this carbene now? Single bond looks like 1 X-type interaction. Carbon makes 4 bonds. So you call that thing a 1 electron donor, and that gets you to 18 electrons again. So this resonance depiction on the left is really like this. And the one on the right looks like this. Whereas the one on the left looks like X2. So notice how if we were to pull this fragment off on the right-hand side, you take this thing off, you're actually removing a neutral fragment here overall. It's a neutral fragment with a lone pair on carbon. That can act as a L-type ligand. Makes it a lot easier to count that molecule's oxidation state. So the oxidation state on the right, you could think about as tungsten 0, D6, chromium, molybdenum, tungsten, have 60 electrons. And we pulled off this carbonyl, neutral carbonyl fragment, carbene fragment, as a 2 electron donor. So that doesn't change the oxidation state of the tungsten when you stick it on there. So that's the same thing as having a negative charge in the metal and then the 1 electron donor representation. So that's tungsten 0. What about this thing on the left? What's that one? The thing on the left makes 2 normal covalent bonds without any of this funny charge business going on. That's tungsten 2. Okay, so you end up with a change in the oxidation state of the metal depending upon the resonance depiction. And this is where things start getting funky and people start asking questions like, well, what's a better resonance depiction? Right? What's the charge on the metal? Is it D4 or D6? The compound doesn't care what you think. It has its own identity. But you can ask whether the resonance depiction on the right or the left is better when that changes the oxidation state. Covalent bond classification doesn't care about any of this stuff. Okay. Let's do some metal-metal bonds here. So metal-metal bonds, especially if you have two metals that are the same metal in a symmetric compound, they don't change the oxidation state because they have the same electronegativities. So the electrons are purely covalent, right? There's no ionic character if the metals are identical. There's no greater or lesser electronegativity. So metal-metal bonds are talked about as not changing the oxidation state of the metal. But they do change the valence. So we've got that manganese compound we looked at before. What's the oxidation state of the manganese here?
Zero.
0. D 7. Manganese starts with 7. Manganese, technetium, rhenium. We got 5 COs, gets you to 10 electrons. A manganese has 7. And then the manganese that's donating 1 electrons brings this total count up to 18 electrons.
Professor, can I ask a question about this? Like,
Yeah.
okay, so this is manganese 0, right? We're checking not the oxidation state, we're checking the valency, or we're checking the oxidation state.
This manganese 0 is a description of the oxidation state.
Okay, so we're just saying because you said that they are symmetric and they're not polar, that they're going to be 0. But
Yeah, because there's no electronegativity difference, and that's how oxidation state is defined.
okay, and these CO5, like the five carbonyls that you have surrounding the complex, they're not doing anything to the oxidation state at all because they're neutral. Is that?
They're neutral 2 electron donors.
Okay. Thank you.
So they do not change the oxidation state. Now note that the oxidation state formalism implies something about the number of unpaired electrons. But we know that this manganese-manganese complex here forms a bond by pairing the unpaired electron sitting in that DZ squared orbital. Right? We did that earlier. These 2 metalloradicals get together and they pair up their electrons. So is there really 70 electrons? I would say no. So the oxidation state formalism kind of doesn't handle this situation very well. Manganese is monovalent. So people tend to talk about clusters of metals by saying that, you know, if you have any metal-metal bonding interactions, you just pair up your electrons to get to 18. Okay, so like rhodium 4 dodecacarbonyl is rhodium 0 D9. Okay, there's no X-type interactions of any kind in there from the perspective of the polar ones anyway. This thing is a pyramid of rhodiums. So if you wanted to ask, well, how many unpaired spins do we have here? You just count the number of electrons needed to get to 18. And then the metal centers will pair up their electrons until that's achieved. So when you're in this situation and you're looking at metal-metal bonded complexes, you might draw more than one metal-metal bond. You might draw a metal-metal double bond to raise the total electron count of the metal centers to 18. Sometimes people just draw metal-metal bonds in there because it makes the drawing look nice. But then you have to start asking more seriously, what's going on? Are there electrons pairing? What are the interactions really like? The real representation of structures like that is mostly about molecular orbital theory. It's not so much about localized bonding. So whenever I look at these sort of things, I kind of scratch my head a little bit and wonder about the utility of all this localized representation. Okay, all right, so I'm going to stop there. And happy to stick around. I have 2 minutes. I have another meeting at 1 o'clock for which I cannot be late. So I will